Hi, in this video we are going to talk about time complexities and running time of algorithms. So let's get started. First of all, let me tell a few words about the big O notation, or this is the Landau notation. It describes the limiting behavior of a function when the argument tends towards a particular value, or usually infinity. A description of a function in terms of big O notation usually only provides an upper bound on the growth rate of the function, and there are several related notations using the symbol sigma and theta to describe other kinds of bounds on asymptotic growth rates. The lambda is usually denotes the lower bound. The big O notation provides an upper bound. And the concrete definition is that let f and g be two functions on some subset of real numbers, then we say that fx is equal to big O gx as x tends to infinity if and only if there is a positive constant c such that for all sufficiently large values of x, the absolute value of fx is at most c multiplied by the absolute value of gx. And there are two important rules that if fx is a sum of several terms, the one with the largest growth rate is capped and all others omitted. For example, we have O n plus log n. Then because n is the bigger it's as far as the growing rate is concerned, then it's going to be equal to big O n. And if fx is a product of several factors, any constants are omitted, so we have a constant multiplied by the n, it equals to ordo n. And it's proved to be very important because when we are going to talk about algorithms, for example, when we have to iterate through a list, we have to make swaps, for example, then iterate through again, then we usually face the first rule that we have ordo n plus log n, and we can simplify it with the help of this rule. And the second rule is proved to be very important, for example, radix sort, that we are going to iterate through a list once, twice, or 10 times, for example, then these constants, the 1, 2, and the 10 factor, can be omitted, and it's going to be reduced to, for example, linear time complexity as far as the radix sort is concerned. So here's a graph, a good illustration about it, that we have two functions, the fx and the gx. The fx is denoted with red, the gx is denoted with blue, and we can see that from approximately 4.5, so from x0, the fx is going to be equal to a c times gx. So this is the concrete definition we've been talking about here, that fx is equal to ordo gx. So that's it. And let me tell a few words about big O complexities in the main. If we plot the operations in the function of elements, then there are approximately 6 very important complexities, or 7. The constant time complexity, it is the fastest complexity we have known so far. And for example, if you want to swap two numbers in a sorting algorithm, it can be done in constant time complexity. Then a very efficient algorithm is the so-called logarithmic ordo log n. For example, if you want to search for something in a sorted array, we can use the logarithmic or binary search. Or for example, if you are familiar with binary search trees, we can find anything in logarithmic time complexity. So it's very efficient. Then another efficient approach is the linear time complexity. It is not so bad. For example, we want to find the maximum element in an unsorted array, then we have to iterate through all of the elements one by one. It definitely has linear time complexity. Then most of the divide and conquer sorting algorithms, merge sort, quick sort, heap sort, we are going to talk about it a lot in the coming videos. It has linear arithmetic time complexity. It's not that efficient as linear time complexity, but it's much better than quadratic or exponential algorithms. The next one is the quadratic. For example, bubble sort has a quadratic time complexity, although n squared. Then exponential is definitely not efficient, and factorial is the worst case scenario. So yeah, here are some examples I've been talking about: the swap two numbers, then the search in a sorted array with binary search, it has logarithmic time complexity. Then linear time complexity, we usually want to reduce most of the algorithms to linear time complexity or to logarithmic time complexity. With the help of, for example, hash map, constant time complexity can be achieved, but it's very hard, very hard to construct the hash function to be as precise to get the constant time complexity. And ternary search tree is a very good approach to solve problems in constant time, but usually logarithmic time complexity is very good as far as algorithm running times are concerned. So merge sort, quick sort, and heap sort has n log n linear arithmetic time complexity. Bubble sort has n squared. Then the traveling salesman problem with the help of dynamic programming, it has an exponential time complexity, 2 to the power of n. And the traveling salesman problem with brute force search has ordo n factorial. It's very bad, and usually for the last two we need heuristics, and heuristics, we just want to find an approximate solution. These problems are very hard to solve exactly, and that's why we usually just want to find a good solution, an approximate solution. So we have to find some heuristic, and with the help of these so-called heuristics we can find a solution in polynomial time, so n squared, n cubed, and so on. Anyways, if you are not familiar with traveling salesman problem, we are going to talk about it in a lot in the coming videos, but the main problem is that there are several cities, for example n cities, and we want to start from a given point. We want to end up in the given point, and we want to visit each city exactly once. This is the so-called traveling salesman problem. It is very hard to solve exactly, but there are several heuristics, good solutions. With the help, we can solve this problem very quickly. As far as the complexity classes are concerned, we have the so-called P, the NP, the MP complete, and the MP hard. The P stands for polynomial, and most of our algorithms are in this class as far as searching are concerned, binary search tree operations are concerned, ternary search trees are concerned, or we want to sort an array, for example. We want to find the shortest path for a given graph between two vertices. All of these problems are in polynomial. Then the NP stands for non-deterministic polynomial. Then the most important problem is whether P is equal to MP or not. Then the MP complete and the MP hard is the hardest problems in the 21st century will be known. So let me tell a few words about both of them. The polynomial is one of the most fundamental complexity classes, contains all decision problems that can be solved by a deterministic Turing machine, and P is the class of computational problems that are efficiently solvable, so we can solve it with the help of any kind of sorting algorithms in linear time complexity, logarithmic time complexity, or even, for example, as far as bubble sort they are concerned, we can solve it in n squared time complexity, which is not so bad, not so efficient. We can do better, but it's definitely polynomial. So, for example, all sorting algorithms or finding the shortest path, finding the spanning trees are in this polynomial class. As far as non-deterministic polynomial class is concerned, if we have a solution to a problem, we can verify this solution in polynomial time. So we cannot solve the problem in polynomial time, but if we find a solution to the problem, we can verify it in polynomial time by a deterministic Turing machine. So for instance, where the answer is yes, we have efficiently verifiable proofs of the fact that the answer is indeed yes in polynomial time, quite fast. So the complexity class P is contained in NP, and the most important question, as I said earlier, whether N is equal to NP, is it true or not? So for example, non-deterministic polynomial problems are integer factorization. If you are familiar with encoding, most of the encoding we use is rely heavily on this NP problem, that we are not able to factor an integer fast, so we don't have any good algorithms. If we find the solutions, it's very easy to verify the solution, because we have to multiply the two numbers. It can be done in polynomial time, but if we don't know the answer, we are looking for the answer, it's very hard. And the RSA code, if you are familiar with these kinds of topics, then this typically relies on the NP hard problems. And the traveling salesman problem is an NP hard problem. The NP complete problems is a decision problem in NP complete when it is both in NP and NP hard, although any given solution to an NP complete problem can be verified in polynomial time. There is no known efficient way to locate a solution in the first place. So we usually just look for an approximate solution. And in this situation, as I said earlier, heuristics are needed. For example, the Chinese Postman problem, graph coloring, Hamiltonian cycles. All of these, for example, graph coloring, we usually use the greedy approach. We just want to find the nearest neighbor, and we usually end up in a local minimum, but it's a good approximation. Chinese Postman problems and Hamiltonian cycles are usually relied on much complex approaches such as the simulated annealing or genetic algorithms. It's becoming more and more popular with artificial intelligence and machine learning. These are very good topics. And the NP hard problems, this is a class of problems that are at least as hard as the hardest problems in NP. And a problem H is NP hard when every problem L in NP can be reduced in polynomial time to H. As a consequence, finding a polynomial algorithm to solve any NP hard problem would give polynomial algorithms for all the problems in NP. So it would be the best if any of us, any of you, could find a polynomial algorithm to solve any NP hard problem, such as the halting problem. Then it means that all the problems in NP could be solved in polynomial time very efficiently, very fast. So the so-called holding problem is such a NP hard problem, and the problem itself is that this is the problem which asks, given a program and its input, will it run forever? And that is a yes or no question. So this is a kind of a decision problem, but it is very hard to solve. So that's all about the introductory video on time complexities and algorithmic design. Thanks for watching.